This is a final run through of all the topics for the higher tier of Chemistry Paper 2 for AQA GCSE Combined Science based on the 2022 Advanced Information. In other words, I've missed out the one topic from the Not Assessed section, and I've only talked about the 2 listed required practicals that are listed in that information. Anything that's on a green slide is a major topic which is expected to make up high tariff questions, although to be honest that kind of covers most of the paper. The few lilac slides are in here are topics which haven't been removed from the paper, but they don't fall into one of those major topics. Since so little content has been removed from the paper, I've mainly reused my old recording, so I'm sorry in advance that the sound is going to jump slightly when it switches from the new recording to the old. Before we dive into the chemistry content, I want to remind you of a few little things. Firstly, it's really important that you're writing in black ink and staying within the box on the exam paper, because your script is going to be scanned, and so if you don't do these 2 things, there's a risk that you don't get credit for something that you've written because your examiner just couldn't see it. There aren't very many calculations in paper 2 of chemistry, but do watch out for any sneaky units where there might be an additional mark for converting between different forms. For any extended response questions, or really any question on the exam paper, bullet points are a really good idea. You don't get any credit for answering in full sentences, and by writing in bullet points you're more likely to stick to 1 marking point per line, and that makes it much easier for your examiner and avoids them potentially missing something that you've written. Any question that has the command word evaluate has 1 common mark scheme, and this says that you need to have a strongly justified conclusion in order to get all of the marks. That means it's really important that you come down on one side of the fence or the other. You're likely to have also been given some information, such as in a table, and it's really important that as you compare the values in the table that you're trying to add some value. So you might have something like comparing some different fuels and you're looking at how much carbon dioxide is being released, and you want to be saying, oh, this fuel releases 5 times more, not just this fuel releases a lot. So you want to have that comparative aspect in there. If you do end up having to write a method for one of the required practicals or for any practical activity, make sure that it's written in a logical order. You might want to use a numbered list so that if you forget something it's easy to slot in. And make sure that somebody following it would actually be able to get the data to answer whatever question it is you're trying to answer. So make sure that you have told them to change the independent variable, to record the dependent variable, and to control the control variables by keeping them the same. There are also plenty of marks available for these working scientifically skills, which go across all 3 disciplines of science. So this includes things like being able to name the variables for any practical activity, knowing the difference between repeatable and reproducible data, which will both show you the same pattern in the data, but for repeatable, it's you using the same method that you used again, whereas for reproducible, it could be a different group of scientists or a subtly different method that still examines the same question, but again, we're seeing that same pattern. Resolution is about the equipment you're using and what the smallest difference in data you can detect is, and we like computerised methods because they are accurate, rapid and sensitive. If you have to plot some data onto the graph, which is particularly likely to come up in Unit 6 for the rates topic, make sure that you are putting all of the data on there. It's really common that people accidentally miss out the first point, particularly if it's at 0, 0, and make sure that your line of best fit does whatever the data does. I know that in GCSE maths you're only assessed on straight lines and straight lines are best fit, and so people think that that's going to be the case for GCSE science as well, but it's not. So if your data does curve, make sure that your line of best fit curves as well. There always ends up being a bit of a buzz on social media after at least one of the science exams because there's been a significant amount of maths content assessed, and this comes as a surprise to many people because apparently they don't realise that 20% of the marks in GCSE science are for mathematical skills. So you're expecting to find that 1/5 of the marks on the paper are for doing things that you would have to be assessed on in GCSE maths. So I've summarised these here, but for the full list you can see chapter 9 of your specification. I'd recommend spending a little bit of time making sure that you are familiar with what each of these terms means and just brushing up on them a little bit, because there are often individual marks for things like giving your answer in standard form that it's really easy to miss out on. I'd also recommend that when it actually comes to the exam that you mark these to yourself in some way, so maybe draw an asterisk next to the instruction or highlight it, because it's really common that people will do quite an extended calculation and then miss out on the last mark because they haven't given their answer to the right number of significant figures or they haven't expressed it as a percentage or something like that. The first topic in the second paper of AQA GCSE chemistry is the rate and extent of chemical change. The rate of a chemical reaction is its speed, how fast it's going, and we can measure this in 2 ways, either how quickly the reaction is using up the reactants or how quickly it is making products. There are two calculations that you can use to work this out, but they're essentially the same thing. An amount of one of the chemicals divided by the time that it takes to either make it or use it up. Either one of those amounts can be a mass in grams or a volume in centimetres cubed. If you're taking higher tier, you should also be able to express rate in moles per second. But whichever one of these you're working with, you're still using the same calculation, an amount divided by a time. To take an example, if we had a reaction that produced 20 centimetres cubed of gas in 2 seconds, then I would do 20 centimetres cubed divided by 2, and that would give me 10 centimetres cubed per second, which is the rate. It's worth remembering that even if you forget how to calculate this rate, as long as the exam board have given you the units, which they often do, then the calculation is actually wrapped up inside it. The word per means divided by, so if the units are centimetres cubed per second, you need to take centimetres cubed and divide them by seconds. You need to be able to plot raw data onto a graph and interpret graphs that the exam board have given you. On a rate graph, the gradient or the steepness of that graph can be used to tell you the rate of the reaction. So in this instance, the reaction represented by the purple line has got a faster rate than the blue reaction because the line has a steeper gradient. We can also say that for both of these reactions, the rate is constant because the gradient isn't changing. On a curved graph like this one, the rate is changing, and we can make a qualitative statement about how at the start of the reaction the rate is faster because the graph has a steeper gradient, and then gradually the rate slows down. By calculating a numerical value for the gradient, we can calculate the rate. So we're actually still using the same formula that we used before, but even if you forget that, you know from GCSE maths that to work out the gradient, you divide the change in the y-axis by the change in the x-axis. So here we divide 5 grams by 10 seconds to get a rate of 0.5 grams per second. For a curved graph like this, we can still use the start and the end of the graph to work out an overall or mean rate. So here the graph increases by 6 grams in 10 seconds, giving us a rate of 0.6 grams per second. You can also draw tangents to calculate the rate at one particular timestamp. A tangent is a line that only touches the graph in one place. To be as precise as possible, make sure that your tangent is as long as you can draw it, and ideally use a transparent ruler or put your ruler on top of the curve so that you can see the size of the gap on either side, because we want it to be the same size on both sides. So here at 4 seconds, the tangent rises from 2 to 9 grams, which is a change of 7 grams, and that takes 10 seconds. So the rate is 0.7 grams per second. But if we draw another tangent at 7 seconds, where the graph is flatter and we know the rate is slower, we can see that here the mass only changes by about 2 grams in 10 seconds, so therefore the rate is 0.2 grams per second. Now we've talked about how to calculate a rate, we need to think about why it might change, and to explain that we need to use collision theory, which is the idea that chemical reactions only happen when the reacting particles collide with each other, so they bang into each other, and when they have sufficient energy. And we call this minimum amount of energy the activation energy. There are 5 different ways that you can speed up a rate of reaction, and these are by increasing the pressure, increasing the concentration, increasing the surface area, increasing the temperature, or by adding a catalyst. You can increase the pressure in 2 ways. One is by increasing the number of particles in a container. So if you imagine blowing up a balloon or pumping up a bike tyre, where you're physically adding more particles. And the other is by making the container smaller, because the pressure is caused by the particles bouncing off the walls of the container they're in. If the particles are in a smaller box, or if there are more particles in the same box, then it's much more likely that the particles will collide with each other and therefore a reaction can happen. So we would say that increasing the pressure will increase the rate because the particles will collide more frequently. And frequently is such an important word, because the important thing is not just that they collide more, but that they do more in the same amount of time. So it's really important for all of these rate questions that you're talking about particles colliding more frequently or more often or more times per second. Concentration is very similar to pressure, but it applies to solutions rather than gases. Overall though, it's the same idea. When we have a higher concentration, there are more particles in the same space, and therefore they're more likely to collide, so they collide more frequently, and therefore we have a higher rate of reaction. Talking about surface area can sometimes confuse a few people. The thing you need to understand is that as you cut something into smaller pieces, you increase the overall surface area. That can be tricky to get your head around because you're thinking, well, it's a smaller piece, so surely the surface area is smaller. But we're talking about all of the pieces combined together. It might be easier if you talk in terms of the surface area to volume ratio, because for the same amount of stuff, we now have a bigger surface area. This might be easier to visualise in 2D. If this green block represents a piece of magnesium sat in some acid, the acid can only react with the outside rim, this 16cm perimeter. But if we cut each side into two, then we expose all these central parts that can now react as well. Even though each one of those pieces individually is smaller than the original square, when we put the four of them together, they still have the same area, but a larger perimeter. So we can increase the rate of chemical reactions by cutting metal into smaller pieces or grinding up marble chips to make powder. Again, this will increase the frequency of collisions. Increasing the temperature increases the rate of reaction in two different ways, and they're both linked to the fact that the particles have more energy. Firstly, increasing the temperature will increase the frequency of collisions. The particles have more thermal energy from being heated, and that's transferred to kinetic energy, which means that they move faster. If you think about walking down a corridor versus running down it, if you're moving at a higher speed, it's much more likely that you'll collide with somebody else, and the same is true of the particles. Because they're moving faster, they collide more frequently. But also, we can think about that second part of collision theory. As well as colliding, the particles need to have a minimum amount of energy called the activation energy. If all of the particles in a reaction have more energy, then it stands to reason that more of them will reach that minimum threshold. Finally, to speed up the reaction, we can add a catalyst, which is a chemical that speeds up the rate of reaction without being used up or changed itself. It's important that you understand that catalysts are chemicals. We sometimes see in exams people writing about heat acting as a catalyst, and that's not true. This has to be a chemical that we're adding. Enzymes are an example of a biological catalyst, which just means a catalyst made by a living organism. The way that catalysts work is that they provide an alternative pathway for the reaction to happen, which has a lower activation energy. To visualise this, imagine that you're trying to visit a friend who lives on the other side of a mountain. For you to get up and over the mountain takes a certain amount of energy, and that represents the activation energy. Now, there isn't really much we can do to make the mountain take less energy to climb. But if there was an alternative route where you could walk around the bottom of the mountain, that might take less energy. And this is exactly what a catalyst does. It's not that it changes the amount of energy to get over the mountain, it just provides an alternative route that needs less energy. In Unit 5, you learned how to draw and interpret these energy profile diagrams for reactions. So this is an example of an exothermic reaction where the reactants have more energy than the products. And we can draw an arrow representing the activation energy, the amount of energy required for this reaction to start. So if this is my diagram without a catalyst, then when I add a catalyst, the reactants and products will have the same amount of energy, but in between them, we won't need as big of an activation energy. So the very top of that energy profile will be lower, and if I was going to label the activation energy, I'd label it here. The first required practical that comes up in AQA GCSE Chemistry Paper 2 investigates what happens to the rate of reaction when we alter the concentration. This is a two-part investigation. You need to be able to describe both how you would do this using a method where you collect gas, and also how you would do it with a method that involves turbidity. The first of these could be any chemical reaction that releases gas, but the most normal ones to do would be either adding magnesium or marble chips to some acid. For each one of these, we need to be measuring the amount of gas that's produced in a certain amount of time. There are two ways you can do this. Either you can collect gas over water by using an upturned measuring cylinder full of water, so as the gas is produced, it pushes the water out and you can read off the measuring cylinder how much gas has been made. Or you can use a gas syringe, which is a little bit easier, but also they tend to be quite expensive and lots of schools don't have them available for use. Whichever one of these methods you describe, it's vital that you mention that you're taking readings at regular time intervals, say every 5 seconds or every 10 seconds, as if you don't do this, you won't be able to calculate the rate. As with all of these investigations, you also need to be able to describe how you would keep other variables controlled in order to make the experiment valid. So in this instance, we have to change concentration because that's the point of the required practical. So I'd be wanting to control things like the volume of the solutions that I'm using and the mass of whatever it is that I'm adding. For the second part of the required practical, you measure a reaction which becomes turbid, meaning cloudy. Every school I know of uses the reaction between hydrochloric acid and sodium thiosulfate for this, but whichever reaction you do, there will be a solid precipitate formed. So if you're given a chemical symbol equation, you want to look for the product which has a state symbol which says S next to it. This is what makes the reaction become turbid. The classic way to monitor this is by timing how long it takes for a cross on a piece of paper to disappear. The faster it disappears, the higher the rate of reaction. This is a perfect opportunity to talk about how subjective human judgment is and how it would be a better experiment if we used a light sensor hooked up to a computer. In some chemical reactions, it's possible for the products to react together to make the original reactants, and we call these reversible reactions, and you can recognise them because rather than a normal arrow between them, we have this funny double-headed reversible reaction arrow. It's possible to change the direction of the reversible reaction by changing the conditions. You should also know that if a reversible reaction is exothermic in one direction, then it will be endothermic in the opposite direction, and there is a named example of this. If you heat up some hydrated copper sulfate, which is blue, you can make a white powder called anhydrous copper sulfate, and that's an endothermic process. You have to heat it in order for it to happen. If you take some anhydrous copper sulfate and you add some water to it, then you can turn it back into the hydrated copper sulfate, and this is an exothermic process. It will get hot on its own. When a reversible reaction happens in a closed system, it will eventually reach a point called equilibrium, and this means that the forward and backward reactions are happening at the same rate or the same speed as each other. When this happens, the concentration of the reactants and products will stop changing. Be careful though, this doesn't mean that the reactants and products are present at the same concentrations as each other, just that their concentrations have stopped changing. So if I was going to look at a graph of a reversible reaction reaching equilibrium, I could identify equilibrium as the point where the graph completely flattens out. If you're taking higher tier, then you need to be able to use Le Chatelier's principle in order to explain how we can move the position of equilibrium by changing the reaction conditions. Le Chatelier's principle tells us that if a system is already at equilibrium and a change is made to any of the conditions, then the system will respond to counteract that change. That basically means whatever I try to do, the system will try to undo. So if you add a reactant, the system will remove it, and if you heat a reaction, the system will try to cool it. Often with these questions, the exam board won't actually give you the names of chemicals because they don't want to confuse you with reactions you haven't heard of, so they quite often just refer to a blue copper compound or a pink cobalt compound. So in this reaction, a blue copper compound reacts with hydrochloric acid to make a green copper compound and water, and this is a reversible reaction. If I add more hydrochloric acid, I know that Le Chatelier's principle has told me that the system will shift to counteract that change and get rid of the hydrochloric acid. The only thing that the system can actually do is make either the forward reaction or the reverse reaction happen faster. So whichever reaction removes hydrochloric acid, that's the one that will go faster. That's the one that we say will be favoured. So in this instance, the forward reaction is favoured. That means that the equilibrium shifts to the right. In other words, I'm making more of the products. Therefore, there'll be more of the green copper compound formed, and my solution will start to look greener rather than bluer. The second reaction condition that we can change is pressure. Pressure, remember, is caused by particles colliding with the walls of the container that they're in. So the more particles there are in a container, the higher the pressure will be. If we increase the pressure, this will favour whichever side of the reaction has fewer molecules on it. To answer a question about pressure and equilibrium, I need to look at the chemical symbol formula and identify which side of the equation has more gas molecules on it. In this example, I have 3 moles of gas in my reactants, but only 2 moles in my products. So the reactant side is a high pressure side and the product side is a low pressure side. If I decrease the pressure, Le Chatelier's principle tells me the system will shift to counteract that change and increase the pressure. So it's going to move the equilibrium towards the higher pressure side, which here is my reactants. So here I would say that the backward reaction is favoured because there are more molecules on the left. I need to actually point this out and explicitly tell the exam board that I know that this is why the equilibrium is going to shift. So the equilibrium will shift to the left, and therefore the yield of sulfur trioxide will be lower. We said at the start that if we heat up a reaction at equilibrium, the system will shift to try to cool it back down again, and the way it does this is by favouring the endothermic reaction. It's very likely in a question such as this that you may be told that the forward reaction is endothermic, but not told anything about the reverse reaction. You are expected to know that for a reversible reaction, one way will be exothermic and the other way will be endothermic.
So in this instance, the forward reaction is going to be favoured because that is what will cool my reaction back down. And I need to tell the exam board that I know that this is because the forward reaction is endothermic. Therefore, the equilibrium shifts to the right, and therefore what I will see or observe is that my mixture will turn white. The second topic in AQA GCSE Chemistry Paper 2 is organic chemistry, which starts off talking all about crude oil. So you need to know that crude oil is a finite resource, which means that it's going to run out, and it's found in rocks and made from the remains of ancient biomass, which is mainly plankton that was buried in sediment. So basically we're talking about lots of sea creatures that died and then mud and sand fell on top of them and turned into rocks over millions of years under a lot of pressure, and meanwhile they turned into fossil fuels like crude oil. It's a mixture of hydrocarbons, so compounds that are made of hydrogen and carbon only, absolutely nothing else, and those hydrocarbons are mainly a type called alkanes.
Alkanes are an example of a homologous series. This is a group of compounds that have similar chemical properties, and the reason they have those similar chemical properties is because they have the same functional group. So the functional group is a small number of atoms that are bonded together, and they have a particular kind of chemistry that we see in all the members of that homologous series. The members of a homologous series will also have the same general formula, so this is like CnH2n plus 2 for alkanes. For combined science, the only homologous series that you need to know about are the alkanes and the alkenes.
You should know that the names of the first 4 alkanes are methane, ethane, propane and butane, and I like to remember this by using the mnemonic most elephants prefer bacon. The general formula for alkanes is CnH2n plus 2. So what this means is that if we give you any number of carbons, say 8 carbons, we can then use that for n to work out how many hydrogens there should be. So 2 lots of 8 plus 2 gives me a total of 18 hydrogens. These alkanes are all examples of small covalent molecules, and that means that between the molecules there are weak intermolecular forces. As with all small covalent molecules, the larger the molecule is, the stronger these forces are. This means that as alkanes get bigger, they have higher boiling points. They also have higher viscosity, which means sort of stickiness, and they become less flammable. Due to the differences in boiling points, the different alkanes that are mixed up together in crude oil can be separated out according to their boiling point by using a process called fractional distillation. In fractional distillation, a mixture of liquids is added to a fractionating column. At the bottom of the fractionating column is a furnace or a heat source which heats them all up to an incredibly high temperature. For the fractional distillation of crude oil, this tends to be somewhere in the region of 400 degrees C. At this temperature, almost all of the alkanes are going to evaporate. As they travel up the fractionating column, there's a temperature gradient. In other words, the nearer you are to the heat source, the hotter it is, and as you go higher, it gets cooler and cooler. As each alkane reaches a height that corresponds to a temperature where it can condense, it turns back into a liquid, and this allows you to separate the liquids and use them afterwards. Fractional distillation of crude oil is used to provide fuels and feedstocks for the petrochemical industry, which are used to make solvents, lubricants, polymers, detergents, and of course, fuels. In order to release the energy from these fuels, they are combusted or burned in oxygen, which is a kind of oxidation, and this releases carbon dioxide and water, as well as a huge amount of energy. You need to be able to write balanced symbol equations for the complete combustion of alkanes. Complete combustion means that they're burning insufficient oxygen for all of the carbon and all of the hydrogen to be fully oxidised. So we're always going to make carbon dioxide and water. If you're not very confident with balancing symbol equations in general, then it's worth learning a method that will work just for the complete combustion of alkanes. Firstly, you're going to look at the number of carbons in the alkane. Here we have propane, so it has 3 carbons. Now, because the symbol equation has to balance, if I have 3 carbons on the left, I must have 3 carbons on the right. And the only molecule on the right that contains carbon atoms is carbon dioxide. So I need to have 3 carbon dioxide molecules. So I'm going to take this 3 from the propane and put it as a coefficient in front of the carbon dioxide. Now I'm going to look at the hydrogens. In this propane molecule, I have 8 hydrogen atoms. And I'm going to make water molecules which each contain 2 hydrogen atoms. So I actually need to take that 8 and half it. So I'm going to put a 4 in front of the water. Now I need to work out how much oxygen I need to make this balance. So I need to add up all of the oxygen atoms on the right hand side. Remembering, of course, that there are 2 oxygen atoms in every carbon dioxide molecule. So that's 2 lots of 3, so that's 6 atoms in total. And then each water molecule only contains 1. so that's another 4 atoms, giving me 10 in total. Now, since oxygen goes round as divalent molecules, O2, the total number of molecules is going to be half of that. So I add up all of the oxygen atoms on the right to make 10, I divide it by 2 to get 5, and that's my number of oxygen molecules. Now, I should probably point out that this method is going to work beautifully provided you have an alkane with an odd number of carbon atoms in it. It will still work if you have an alkane that has an even number of carbon atoms, but the number of oxygen molecules you get out will not be a whole number, so you might need 4.5 or 5.5. And although when we get to A-level chemistry we use halves as coefficients all the time, at GCSE we tend not to, we tend to stick to whole numbers. So if that's what you've been taught and it's a little bit confusing for you, there is quite a simple fix. Let's take this butane molecule here, which has 4 carbon atoms in it. If it completely combusts in oxygen, it's still going to make carbon dioxide and water. But to avoid that situation where I need a half number of oxygen molecules, before I start, I'm going to double up. So I'm going to start with 2 butane molecules. And this is the same thing that I would do for any situation where the alkane has an even number of carbon atoms. So I'm going to look at my 4 carbon atoms there, but then I'm going to remember that I have 2 of these molecules. So in total, I now have 8 carbon atoms, and I'm going to make 8 carbon dioxide molecules. Then likewise, I look at these 10 hydrogen atoms, but because I have 2 molecules, that makes 20 in total. And then I half it, so I'm back to 10, so that's 10 water molecules. And then again, I count up the 16 oxygen atoms in the carbon dioxide and the 10 oxygen atoms in the water, which makes 26 in total, and if I divide 26 by 2, I get 13 oxygen molecules. We've already described that crude oil is a mixture of hydrocarbons of all different sizes, and one problem that we encounter is that there's a really high demand for the small alkanes because they make excellent fuels, but actually crude oil contains large amounts of the much larger alkanes which don't have nearly as many uses. So we use a process called cracking, which is a type of thermal decomposition. In other words, it uses heat to break down large molecules. And what cracking does is it breaks down long alkanes into shorter, more useful alkanes, and also another group of molecules called alkenes. You may be asked to complete symbol equations for cracking reactions, but these aren't nearly as intimidating as they look. In the first style of question, we're literally just counting up the numbers of carbons and hydrogens on the left and right of the equation and making sure that they balance. So if I know that there are 25 carbons and 52 hydrogens in my reactant, then there must also be 25 carbons and 52 hydrogens in my products. So if I know that one of my products contains 10 carbons and 22 hydrogens, I can just take those away from the numbers on the left, and therefore I can work out that my second product is C15H30. Another style of question might tell you what the products are, but not how many of them there are. So in this instance, I need to calculate how many ethene molecules are required to balance the equation. So again, I've started with 25 carbons and 52 hydrogens, and I can subtract the nonane that's already been listed as a product. That leaves me with 16 carbons, and I know that there are 2 in each ethene molecule. So therefore, I must have 8 ethene molecules. There are 2 types of cracking that you need to be able to describe the reaction conditions for, and at GCSE, neither of them mention pressure, which is a really common misconception. It might help if you remember that you've probably either done or watched a demo of cracking in the GCSE classroom, and so there isn't anywhere in that room that you can control the pressure. In catalytic cracking, we vaporise the alkane and pass it over a hot zeolite catalyst. In steam cracking, there's still a very high temperature, but rather than using a traditional catalyst, we use steam. We've just said that in cracking we make 2 types of molecules, the alkanes that we've already met and these new alkenes. Alkenes are more reactive than alkanes, and this is because of the double bond that is their functional group. Each alkene is only going to contain 1 double bond. You shouldn't be replacing all of the carbon-carbon bonds in the molecule with double bonds, you just need 1 of them. In order to test for an alkene, we add an orange liquid called bromine water, which will turn colourless in the presence of a double bond. Unit 8 is the chemical analysis unit, which starts out talking about pure substances. A pure substance in chemistry is a single element or compound, not mixed together with anything else. That's different from everyday life, where we might talk about something like pure orange juice because it hasn't had anything added to it, even though it's a mixture of hundreds of different compounds. Pure substances melt and boil at specific temperatures, so you can use a databook value to figure out whether a substance is pure. For instance, we know that pure water boils at exactly 100 degrees. So if I have some water and it boils at a temperature that's not 100 degrees, well then it's not pure. Formulations are mixtures that have been designed as a useful product. They contain really carefully measured quantities of all of the ingredients. Examples of formulations include fuels, cleaning agents, paints, medicines, alloys, fertilisers and foods. Another way that you can identify whether a substance is pure and which different substances it contains if it's not pure is by using chromatography. There are several different types of chromatography, but in GCSE you're most likely to have met paper chromatography, which forms the basis of the required practical. All types of chromatography are used to separate out mixtures and then to analyse what is in them. They all make use of a stationary phase, which remains still, and a mobile phase, which moves through the stationary phase, transferring the sample. In paper chromatography, the stationary phase, which doesn't move, will be the piece of chromatography paper, and the mobile phase will be a solvent, and you're most likely to have used water. And that water moves through the chromatography paper, and it will transfer your samples, which tend to be inks or dyes or something. The substances are going to be separated out based on how well they are retained by the stationary phase. So basically, how good is the stationary phase at holding onto them? In paper chromatography, this corresponds to how soluble the substance is in the solvent. A very soluble substance will travel with the solvent for a long distance, whereas a less soluble substance will be deposited on paper after a shorter distance, and something that's not soluble at all just won't even move off the start line. Chromatography is a comparative method. We analyse substances by comparing them to chemical standards, known substances for which we already know the results. This is a bit like fingerprinting. You can't just look at a fingerprint left at a crime scene and know who it belongs to. You need a database of the fingerprints of everybody who'd been in that area, and then you can find out whose fingerprint it was by comparing them. Rather than just eyeballing a chromatogram and saying, well, this spot seems very similar to this standard, we can calculate something called an RF value, or a retention factor value. This is a number between 0 and 1, which tells us more precisely whether two samples are behaving in the same way. It's particularly good for if we don't want to include a sample of the standard on our chromatogram. We just want to look up a number in a book and say, well, is it the same? The RF value is calculated by dividing the distance moved by the sample by the distance moved by the solvent. And of course, the distance moved by the solvent is the maximum distance that the sample could have travelled because it's being carried by the solvent. You can't just have your colour jumping ahead of the solvent front. Since substances have different solubility in different solvents, they will also have different RF values in different solvents. So repeating the chromatogram with different solvents might allow us to separate out substances that have the same solubility in one solvent. Imagine you have a dot on a paper chromatogram made with water that actually contains two different inks, but then when you run the same chromatogram using ethanol, they might separate out. A pure compound only contains one substance, so even if you put it in a whole range of different solvents, you won't split it up into different multiple spots. Paper chromatography is one of your named required practicals, and therefore you need to be able to write a method to explain how it should be carried out. So to start with, you draw a line on which you're going to put your samples, and as you know, it's really important that that line is drawn in pencil, not pen, to stop it from running and interfering with your data. You're going to place the sample of the standards and also the sample you're trying to investigate on that line, and then you're going to put it so that it's just sitting into a beaker of solvent. And it's really important that that solvent is below the line, because if the solvent comes above the line, then rather than being carried up the chromatography paper by capillary action, your sample would just bleed out into the solvent and you wouldn't get any results. You may want to put a lid on top of the beaker to prevent the solvent from evaporating. As we've said, on that start line, as well as your sample, you're going to put some standards that you can compare it to. And then at the end, you're going to measure the distance travelled by everything and use these numbers to calculate an RF value. The next topic is the chemistry of the Earth's atmosphere, which starts off looking at the modern atmosphere. So you need to know that for the past 200 million years, the atmosphere has consisted of about 80% nitrogen, about 20% oxygen, and small amounts of other gases, including carbon dioxide, water vapour, and noble gases like argon. Next, we need to think about the Earth's early atmosphere. Earth's atmosphere first formed about 4.6 billion years ago, and that means we can't be exactly certain what happened because there isn't a huge amount of evidence. Now, your keyword here is evidence. We don't want to just be saying, oh, we don't know because nobody was around to see it. That won't get you the mark. We do know that initially there was intense volcanic activity, and that volcanic activity spewed out lots of carbon dioxide and water vapour, and it made the Earth's early atmosphere quite similar to that of Mars and Venus today. Now, obviously, because there were loads of volcanoes, it was really, really hot. So even though there was lots of water in the atmosphere, there wasn't any on the ground, so there weren't any oceans. There also may have been small amounts of nitrogen and ammonia and methane, and that's important because they were key components in the formation of the first amino acids, without which life could not have formed. As time went on, the Earth cooled down and then oceans formed, so carbon dioxide started to dissolve in those oceans, and then plankton, tiny sea creatures, used that carbon dioxide dissolved in the oceans to make calcium carbonate shells. If you've ever seen the White Cliffs of Dover, they're made of a stone called limestone, and that's made from the shells of dead sea creatures. So that's where lots of this carbon dioxide is locked up in sedimentary rocks like limestone. Also, when they died, some of those sea creatures were turned into fossil fuels, so a lot of the carbon is also locked up in coal and oil and gas. Over time, these processes led the level of carbon dioxide in the atmosphere to decrease quite dramatically. Now, about 2.7 billion years ago, algae started photosynthesizing. Algae are part of the same kingdom as plants. They have chloroplasts and cell walls, but they also include things like seaweeds and microscopic single-celled photosynthetic organisms. These little green cells started photosynthesizing, and as you know, this makes glucose, but it also makes a lot of oxygen, and so levels of oxygen started to rise. And then about 1 billion years later, the first higher plants evolved, and oxygen levels eventually got high enough for animals to evolve too. Next, we get on to greenhouse gases, and first, let's establish this has nothing to do with the ozone layer. The ozone layer is not mentioned at all in GCSE chemistry, so just park it on one side and forget that it exists. You should know that greenhouse gases have something to do with global warming, but we need a little bit more detail here. Firstly, the 3 named greenhouse gases in your specification are carbon dioxide, methane, and water vapour. These are molecules that will vibrate in response to radiation, and they're responsible for the Earth warming up. Having a little bit of them is actually a good thing because it keeps our temperature stable and high enough to sustain life. But unfortunately, we now have too much of them, and so climate change and global warming are happening. These greenhouse gases form a sort of blanket around the Earth, and if you imagine that blanket has holes in it, and shortwave radiation like visible light, UV, gamma and X-rays can get through the holes because they have a short wavelength. However, when that radiation reaches Earth, the Earth absorbs it, and when it re-emits it and gives it back out, it does so with a longer wavelength. So that radiation being emitted is infrared radiation. Now, that infrared radiation is too big to easily pass back through the greenhouse gas blanket. So although some of it will get back through, some of it will be trapped, and instead it warms up the atmosphere and warms up Earth. And these rising temperatures are leading to lots of serious consequences. Now, we need to be specific when we're talking about these. So firstly, as the ice caps melt, this causes sea levels to rise. This can lead to flooding and other extreme weather events, but it's not enough to just say extreme weather events, we need to actually name them. So talking about droughts and hurricanes. Polar habitats are being lost, and with them, many species are going extinct. Make sure that you're talking about polar or Arctic habitats, not just saying habitats. In terms of things that humans do that are making the situation worse, there are 6 key ways that we're increasing the levels of greenhouse gases in the Earth's atmosphere. Firstly, every time we burn fossil fuels, this releases the carbon that's stored in them, increasing carbon dioxide. Also cutting down trees, because that way we're reducing photosynthesis, which removes carbon dioxide from the atmosphere, and also because those trees are a store of carbon. And also digging up peat bogs. Peat bogs form in a similar way to fossil fuels but over a shorter timescale, and again they're a carbon sink. People use peat as fuel or for compost, and so digging up those peat bogs has an impact on carbon dioxide in the atmosphere. Now, you might also have heard, because it's generally kind of hilarious, that farming cows is massively increasing the amount of methane, because cows basically fart out methane. Also, rice farming, because you have to grow rice semi-underwater, and there are bacteria that live in that water in their roots and release methane, and also in landfill, so rubbish dumps. Unfortunately, it's really difficult to model exactly what's going to happen because this is a really complex system. So we tend to come up with models that are quite simplified and miss things out or gloss over them, and then also speculate and guess, and this can be really problematic. And sometimes media coverage can be biased and only tell part of the story. So we need to look for evidence wherever we can. You should know that the carbon footprint is the total amount of greenhouse gases emitted over the life cycle of a product, service or event. And this could be reduced in a number of ways, like buying resources more locally so you don't release greenhouse gases while transporting them in a plane, or by using less energy during manufacture so that you need to burn fewer fossil fuels to generate the electricity. You also need to know, apart from global warming, about some of the other problems associated with using fuels. There are various pollutants released when fuels burn, and as you know, when you burn a hydrocarbon, you release carbon dioxide and water, and carbon dioxide leads to global warming. But if you don't have enough oxygen for complete combustion, then instead of making carbon dioxide, you make carbon monoxide or even carbon particulates, which are basically soot. Carbon monoxide is a toxic gas which stops your red blood cells from working properly, and carbon particulates cause a phenomenon called global dimming, which literally means the sky is getting darker and less light is getting to Earth. Also, almost all fossil fuels have small amounts of sulphur in them as impurities, so when you burn the fossil fuel you also burn the sulphur and make sulphur dioxide. And sulphur dioxide, along with carbon dioxide and nitrous oxides, which can be produced when you burn things at a high enough temperature for super unreactive nitrogen from the atmosphere to react with oxygen, all contribute to acid rain. As well as making acid rain, sulphur dioxide and oxides of nitrogen can cause respiratory problems like asthma. Humans use the Earth's resources to provide warmth, shelter, food and transport. Natural resources, supplemented by agriculture or farming, provide food, timber, clothing and fuels. In addition, we can supplement these resources with synthetic resources, which are those that have been made from chemicals. So for instance, cotton is a natural fibre that grows on a cotton plant, but we now also have fibres like nylon, which is made from chemicals. You should be able to identify whether a resource is finite and is running out faster than we can replace it, so for instance fossil fuels, or whether it's renewable like wood. And you should also know that sustainable development is development that meets the needs of current generations without compromising the ability of future generations to meet their own needs. In other words, using resources in a way that isn't going to mean our grandchildren don't have them to use. Potable water is water that is safe for us to drink, but it's not the same thing as pure water which has nothing else dissolved in it. Potable water needs to have low levels of salts, but it probably does still have some salts in it, and it should also be free of pathogenic microorganisms. But it may have other things dissolved in it, like fluoride ions for dental care or chlorine as a disinfectant. In order to make potable water or drinking water from rivers and lakes, we start by choosing an appropriate source, then filtering it to remove solid matter and sterilising it using chlorine, ozone or ultraviolet light. We can also make potable water from seawater by a process called desalination, which means removing the salt, and there are two ways this can be achieved. Either we can distill it by heating it up until it evaporates, leaving the salt behind, or we can use reverse osmosis, where it's pushed through a membrane. Both of these methods are very energy intensive, and this makes them expensive, which is why countries that have access to sources of fresh water tend not to use them. Potable water can be made from wastewater, including sewage, agricultural waste and industrial waste. In order to make potable water from sewage, we first need to undergo screening and grit removal to remove large objects, then sedimentation to split it apart into sewage sludge, which is semi-solid, and effluent, which is the liquid, and then these are treated with anaerobic and aerobic biological treatment where bacteria digest the sewage and leave us with potable water. Industrial wastewater may also need to have harmful chemicals removed. It's likely that these could come up in the context of an evaluation question where you're asked which method would be easier, so you want to think about the number of steps and the amount of energy involved. If you're sitting higher tier, you need to be able to describe two novel methods of metal extraction, which are increasingly being used to extract copper, because the supply is running out but demand is increasing, so the price is going through the roof. These can both be used on low-grade ores which contain less than 1% of copper. In phytomining, plants called hyperaccumulators are grown on the low-grade ore, and they absorb the copper into their leaves and stems, and then the plants are burned, leaving ash. The copper can then be extracted from the copper compounds in the ash by using displacement or electrolysis. In bioleaching, rather than using plants, we're using bacteria. Both of these methods have the advantage that they involve very low energy. Phytomining is also carbon neutral, and bioleaching has an advantage over traditional chemical leaching methods in that it doesn't involve nasty chemicals like cyanide. However, they tend to be quite slow, and it may still be necessary to remove lots of rock. Companies write life cycle assessments in order to assess the environmental impact of a product they're making by thinking about the extraction of the raw materials, the manufacture, the use and operation, the distribution, and finally the disposal. Some parts of this can be done quite easily and objectively, like how much water is going to be used, but other things are harder. For instance, it can be hard to know exactly how much carbon dioxide will be released as a result of this product being made, because some of that might come down to the amount of electricity that's used when it's being used, and we might not know that in advance. In addition, it's often the company that's manufacturing a product that is writing the life cycle assessment, so they're sometimes not objective and can be misused to reach predetermined conclusions. Reducing our use of raw materials, reusing manufactured products, and recycling products to make new ones can all help to deal with the growing scarcity of resources, growing concerns about our energy usage, and limited space in landfill. You should be able to describe how glass is recycled by colour sorting, crushing, melting and reforming, and how metal is recycled by melting it and recasting. The amount of effort required in recycling is linked to how pure the final product needs to be, and you may also need to evaluate whether recycling is worthwhile in a certain situation.
So that's it for the higher tier of AQA Combined Science Chemistry Paper 2. I really hope that's helped you to feel a bit more confident. Make sure that you go over the required practicals and the working scientifically skills and mathematical requirements for the exam, and then take some deep breaths and go and nail it on Monday. Good luck.